Hi everybody, this is the pre-lab talk for the chromatography experiment. And to start off, I want to go into a little more detail about the different types of substances we deal with in chemistry. There are pure substances, which are always homogeneous or homogeneous. It's the same word, just different pronunciation. Homogeneous means of one kind. So for example, water, elements, something that is a pure substance cannot be separated out of its one compound. So for example, water is always H2O. If you try and separate it further, you would have to separate it into its elements, but any water you have is still one thing throughout. Any element by itself is also a homogeneous pure substance. It cannot be separated further. Mixtures, however, can be separated. They contain one or more, or they contain two or more compounds. There are two different types of mixtures, though. There are homogeneous mixtures that, again, means of one kind, which means they have a uniform composition throughout. So the most common of homogeneous mixtures are solutions, like we've been talking about. For example, salt water, sugar water, lemonade, something that has the same composition throughout the entirety of that mixture. Heterogeneous mixtures, however, are of different kinds, meaning they have multiple phases. And sometimes you can see these differences. For example, if you have a salad or sand in water, you can see the different pieces that are present. Sometimes you can't necessarily readily see these. For example, if you had a mixture of granulated sugar, table salt, and artificial sweetener, all of these are small white crystalline solids. So you might not be able to look and see a difference, but chemically they are in pieces and pockets that are not uniformly spread throughout. So chromatography, what we're talking about today, is going to be looking at separating and identifying mixtures. Chromatography, you can break down the root words into chromo, meaning color, and graphy, meaning writing about. So it's going to be something where we're using colors to differentiate between these different pieces. And I'll get into that a little more. All chromatography involves the use of two different phases, a mobile phase and a stationary phase. What we will be doing in this experiment is called paper chromatography. There are lots of other options like high pressure liquid chromatography or HPLC. There's gas chromatography or GC. There's lots of different detection methods that can be paired with all of these. There's ion chromatography, there's size exclusion chromatography. So there's a bunch of different types, but all of them involve this mobile phase, stationary phase, and how your compound interacts with these two. So for example, if a compound interacts with the stationary phase, it is adsorbed, not absorbed. So adsorbed means stuck to. So if it is interacting with a stationary phase, it will get stuck to it and then lag further behind or take longer to move through. If it is attracted to the mobile phase, then it will get usually dissolved into your mobile phase and travel with it, moving more quickly through your stationary phase. So compounds with the greatest affinity for the stationary phase will lag behind, and that gives you your separation. Now, all compounds will interact with both pieces to different degrees, and that's how we get our separation. So something that interacts with the mobile phase more than the other will move further along, but both will move because they both eventually will interact with your mobile phase. One of the measurements we can take from chromatography, especially paper chromatography, is what's called the response factor or the RF value. The RF value should be relatively constant within the same parameters. So if you're measuring the same compound with the same mobile phase and the same stationary phase, you should get about the same RF value. Again, random error and slight discrepancies may mean the number won't be exactly the same, but it should be very close. To calculate your RF value, we will take the distance traveled by the dye component that we're looking at, divided by the distance traveled by the overall solvent front. So for example, you can see this chromatogram here. And what we do is we will create a baseline that all of our samples will be spotted onto, and the solvent level will be below that. So as the solvent travels up the paper, it will pull the different samples along with it. All of our measurements are going to start from the baseline, not from the bottom of the paper, not from the solvent level, from where we put the samples at their starting point. So that's the baseline. And then up to that sample itself. Depending on how they separate, sometimes they'll separate more of a teardrop shape and you'll have a high concentration of dye at the front. Sometimes they'll separate this way where it's kind of an ellipse and you've got a high concentration in the center. How it separates isn't a big deal as long as if you were taking these measurements, you measure to exactly the same point. So if you're going to measure to the top or to the most concentrated spot or to the furthest behind point, as long as you're consistent across your samples, that'll be okay. So for example here, if we look at the green, the distance from the baseline up to the most concentrated part of that dye is labeled as B. That would be the distance traveled by the dye. The solvent front, if you were doing this, it would be wet along where that black line is, up at the top. And that would be as far as your solvent made it. So you'd measure from baseline to there to get your two values for your RF calculation. So that's all the experiment is. First step is we will be looking at what is the best solvent, the best mobile phase for us to use. So we'll use some food coloring dyes, spot them onto the piece of paper, run them in the 3 different solvents and see which one gives us the best separations. And when you look at the pictures, it will be fairly obvious. If you want to look at the data and get a number to back up just this one looks better, this would be something with varied RF values. If you have all high RF values, that probably just means everything carried along with your mobile phase and you didn't really get any separation. If they're all low values, that means none of your samples traveled off of the baseline very much, and so you probably didn't get any good separation there either. If you have both high and low RF values, that means your samples traveled different distances, meaning they should be separated. And all of this will get reflected in the data you see. Once we figure out which solvent works best with our food dyes, we will then also run this with 2 unknown mixtures to figure out the different components present in them as well. What you will notice, and it's not shown on this example chromatogram, but different samples will often separate into multiple components. So for example, green over here normally actually separates into both blue and yellow components. So if there are multiple components in a line, you will need to measure a distance and an RF value for both components. So the way the data table will be set up is it will be looking at the sample type, for example, on this one, red, blue, yellow, green, that we spotted to the baseline. Then the dye color will also be listed. So if it's a red sample that only has a red component, it would just be red, red, or blue, blue, or yellow, yellow. However, if this green were to separate, you would have green, blue, and green, yellow to indicate that it's separated into 2 different components and the distances and RF values for each of those components. But again, fairly short one this time. Make sure you watch the experiment video, and as always, if you have questions, just let me know.